Hi everyone. My talk is on the gap opening process in the disk with MHD winds. And as you all know, the gas giant planets embedded in the disk produce tidal torques that tend to push the gas away from its orbit and carve a gap in the vicinity of the planet inside the disk. And planet-mediated gap opening in the dust component of the disk is even more efficient, requiring lower planet masses. So the minimum planet mass needed to open a gap in the gas disk depends primarily on the stellar mass, on its aspect ratio, on the disk aspect ratio, and on the poorly known turbulence alpha parameter. The observations show that the disks, the protoplanetary disks, are flat in the millimeter continuum, and they are flared and vertically extended in the scattered light, which means that the turbulence inside the disk is seems to be really low. Because of that, the disks are flat in the midplane, which in its turns means that if the disks are mainly powered, the mass transport and the angular momentum transport is mainly powered by the viscous turbulence. Then the mass accretion rates onto the star must be low, which is not the case. Which means that there is some inconsistency with the observations. So we need some mechanism that transports the mass and angular momentum efficiently, steers up the micron dust, and without making a lot of turbulence in the midplane of the disk. And such a possible mechanism responsible for this kind of disk structure is the MHD wind, magnetocentrifugal wind. And here we are studying the gap opening process in the disk with this MHD disk wind. And as you know, the angular momentum gained by the gas disk due to disk planet interaction results in a outward flow of the gas from the orbit of the planet with this velocity Vp, which tries to open the gap. In its turn, the MHD disk wind tends to close the gap by resulting in an inward gas flow closer to the orbit of the planet with this velocity v disk wind, in which we have this alpha disk wind dimensionless parameter, which is an analog of alpha viscous parameter. So higher this alpha disk wind, stronger are the magnetohydrodynamical winds, this magnetocentrifugal winds inside the disk. And if we equate these two velocities of opening and closing the gap, then we will get instead of the classical condition for gap opening, the modified one, which, as you can see here, has another term, which is because of the disk wind present. And yeah, from theoretical perspective, let's go to the numerics. And what we've done is we modified our 1D code DO by adding this MHD winds, and also the same way modified the 2D Fargo 3D code. And here we define the so-called parameter gap contrast, which characterized the gap opened in the gas and dust disk, which is this peak value of surface density outside of the planet orbit divided by the minimum value of the surface density inside the orbit. And as you can see on this plot, we vary the alpha disk wind parameter by fixing alpha viscous parameter, and for all the values of this alpha disk wind value, or alpha disk wind parameter, the agreement between the 1D and 2D models is within a factor of few, which is really good. And we assume that the gap inside the disk is opened when this gap contrast is equal to 10. So after checking for a few values of alpha disk wind, we conducted a parameter space study on this plot to cover this parameter space. Here we have about 2,500 models, and the solid red thick line here shows the planet mass needed to open a gap inside the gas disk. All the planet values above this line open the gap. We are not showing them here, but below this line the gap is open partially, and the gap contrast is shown here by color. What is important, we compared our results with analytical solution of this equation, which has this form, and it is shown with this magenta dashed line. As you can see, agreement is quite good, and the agreement is about overestimating the analytical solution overestimates our numerical results by about 20 to 50%, which is quite good. What we did next is we checked the gap opening the gap opening masses for the dusty disk, and as you can see here, the mass needed to open a gap in the dust disk is about a factor of 5 lower than for the gas disk when disk winds are weak, and these values are converging for the high disk wind values. It means when for the more or less realistic alpha disk winds, for the planet it is much easier to open a gap inside the dust disk. It means that the lower mass planet is needed to open a gap in the dust disk. So what we will have if we compare two disks which have the same effective alpha parameter, which is the sum of alpha turbulence and alpha disk wind. In one case, we take we have the disk with mass and angular momentum transport powered by turbulent viscosity, and in other case we have the disk which is powered by disk wind. And as you can see, the sum of these values are the same in the disk, but in terms of gap opening masses, as you can see, the difference is huge. We have about an order of magnitude difference in the masses of the planets which were opened the gap in the disk, and as you can see, it is much lower mass planet and is needed when the mass and angular momentum in the disk is powered by the disk wind and not the turbulent viscosity. If we rule out the high turbulent viscosity values, based on the observations, and also rule out the high alpha values in general, because the lifetime of the disk will be much shorter than the observed ones. Then we will end up a result which shows that the gap opening mass is 0.1 Jupiter masses inside 1 AU, and it's more than 1 Jupiter mass beyond about 50 AU. Which means that giant planets must be formed in the outer part of the disk and then migrate inwards. And this result is rather weakly dependent on the stellar mass. So what we get from the observations, if we compare our result with the observations, as you can see here. Here we show observational data of the disks of the planets which are in the system where the disk, protoplanetary disk, is already lost, with these black circles, and with the colored points we are showing the systems where the disks are still present. The planets with disks are still where the disks are still present. And if we take a model where the mass transport is due to the turbulent viscosity, which is this blue line. As you can see, this blue line is which is show the gap opening mass is above this 0.1 Jupiter mass threshold value for the most of the disk. This value is the approximate value for the runaway gas accretion, above which the protoplanetary core will accrete a gas on itself in a runaway manner and will become a giant planet. So what does it mean? It means that the gas giant planets will be made by a runaway gas accretion particularly at any separation from the star. However, if we are now focusing on the disks where the mass transport is due to the disk wind, which are this green line, dashed and dotted lines, then as you can see, the runaway gas accretion will occur only for the planets which are above 10 AU, further than 10 AU from the star, which means that the gas giant planets in the disk with MHD winds are formed in outer parts and migrate inwards, and it is particularly impossible to form hot Jupiters in situ in the small radial distances. In the context of super Earths, which are also observed usually at short orbital periods close to the star, and which are the most common type of the planets observed, gas accretion on these radial distances is expected to be too effective in core accretion theory, and it is really puzzling how the planets are ending up being super Earths and sub-Saturns rather than gas giants if the accretion is so effective. And the answer to this question is that if the mass transport and angular momentum transport is due to the MHD winds inside the disk, then as I said, in this case, the lower mass planet is needed to open a gap, and super Earth may open a gap in the disk before it reached the runaway gas accretion value, gas accretion mass, and it will remain a super Earth or sub-Saturn because when it opens a gap, it separates itself from the gas reservoir in the disk and stay at lower mass. Let me use the advantage of pre-recorded talk and ask you to pause here to read the main conclusions. For more details, please take a look at our paper, and please leave your comments under this video. They are much appreciated, and thank you for your attention.